Okay, so continuing our discussion of curl for right now, we'll get to divergence fairly soon. If I have a real valued function of 3 variables, so little f of x, y, z, I can define a related vector field by taking the gradient of that function. And as we just learned, that's applying this del operator to that real valued function so that I get this gradient. I've just named that f. That's my vector field. And remember, if a vector field is the gradient of some real valued function, that means that f is conservative. So I'm going to now take the curl of f. So that's del crossed with f. Or if you prefer, I could write it as del crossed with del little f. Okay. So I'm taking the del operator and crossing it with the gradient of this real valued function. However I choose to denote it, it's ijk, partial with respect to x, partial with respect to y, partial with respect to z, and then my component functions were partials of f. So partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. So now when I calculate this, if I look at what I'm going to have in the first component, so I cross off this row and column, and I'm looking at that 2 by 2 determinant, I'm going to get the partial squared f partial y partial z. I'm taking the partial with respect to y of the partial with respect to z, minus partial squared f partial z partial y. These are the two mixed second partials that use y and z in different order. This has me doing z first and then y. This has me doing y first and then z. It's a function of 3 variables, but if all of the second partials are continuous, then the mixed second partials are going to be equal, which means that's going to be 0. Now, that is if the second partials, which would be the first partials of this, are all continuous. So let's just say, and the components of f are continuously differentiable. If that's not the case, this may not apply. But generally, the functions we're going to be working with are going to have continuously differentiable components. Okay, if I look at the j's, got to remember to do this one backwards. So I'm going to get partial squared f partial z partial x. So I already had the partial with respect to x, then I took the partial with respect to z, and I'm subtracting this one. So minus partial squared f partial x partial z. Those are the two mixed second partials that involve x and z. So that's going to be 0. And if I look at the k component, I'm going to get partial squared f partial x partial y minus partial squared f partial y partial x. Those are the two mixed partials that involve x and y. So those would have to be 0. So what I get is that the curl of f, if it's conservative, is 0. Now, back in the homework when we were studying conservative vector fields, there was a homework problem that essentially had you prove this, except you didn't know that this was the curl. It had you prove that if you had a conservative vector field, then these two functions would be equal to each other, so their difference is 0. These would be equal, so their difference would be 0. These would be equal, so their difference would be 0. Okay. Now we can phrase that as, hey, if it's a conservative vector field in 3 space, its curl is 0. And that test for conservative vector fields that we have in 2 space, we can extend to 3 space. So if the curl of f is equal to 0 on a simply connected region, we'll just say D, then f is conservative on D. Remember, simply connected means no holes. That's a little bit trickier to define precisely in 3 space, but all of 3 space is simply connected. 3 space minus the origin is not, it has a hole in it. And anything that's a little less obvious than that, I would simply tell you, by the way, this region is or is not simply connected. Okay. All right, excellent. So we can now use curl as our test for whether we have a conservative vector field when we're working in 3 space.